In this problem, we have a semicircular arc made up of an insulating material with charge capital Q uniformly distributed on it, and the arc has radius A. We'd like to calculate the electric potential at the center of curvature of this arc. We're going to also assume that the electric potential is zero at infinity. Let's imagine dividing this arc into small pieces that we can treat as point charges. The potential due to each point charge dq is going to be dv, and the total potential is going to be equal to the sum of all those dv's, which is going to be an integral. So v equals integral of dv. So what is capital V again? That's what I'm looking for. That's the total electric potential at the center of the curvature. And dV is the potential due to each point charge dq that you can see on the picture. That's the green piece of charge that I selected. So let's come up with an expression for dV first. We will apply the formula for electric potential due to a point charge. Here I have applied the formula for electric potential due to point charge, which is equal to charge divided by 4 pi epsilon 0 times distance between the charge and point of interest. Now dq is the charge on my unit element, and a is the distance between each dq and the center of curvature. That's the radius of the curvature. Next, let's express dq in a form that we can integrate over. So basically our integration variable is going to be theta, and I'm going to express dq in terms of d theta. For that, I'm going to introduce the linear charge density lambda. By definition, linear charge density is total charge divided by the length of an object. So for the entire arc, that's going to be equal to capital Q divided by pi times a. Pi times a is half of the circumference of a circle, right? So that's the length of the arc. Now, in terms of the unit element dq, that's going to be equal to dq divided by the width of this element dq. What is that equal to? So the width of this element dq is the arc length here. That is the arc length subtended by the angle d theta. And the arc length formula is basically the subtended angle times the radius of curvature. So this width here is equal to a times d theta. So from the perspective of this unit element, the linear charge density lambda is also equal to dq divided by a times d theta. Let's combine the two and eliminate lambda. That's an intermediate variable that we introduced. So now we're going to get rid of it. And so we're going to combine these two equations and isolate dq. Here I have the right-hand side set equal to one another. As you can see, we have a in the denominator on both sides, so those will cancel. And if we rearrange this equation to solve for dq, here's what we get. And here's dq. It's equal to capital Q divided by pi times d theta. Now, pause for a second. Does this make sense? Physically, is it meaningful? Now, I have charge on one side, dq. The dimension of on the left-hand side is charge. On the right-hand side, what do I have? Capital Q, that's charge, divided by pi, that's just a number. D theta, again, that doesn't have a unit. So the dimensions on both sides should be the same, and they are the same. Each dimension is just electric charge. So let's go ahead and go back to our formula for electric potential and substitute this expression. Now I have my integral expressed in terms of a variable over which that I can actually integrate, and that's d theta. Now let me also put the lower and upper bounds for my integral. This is a semicircle, so theta runs from 0 all the way to pi. This is a very straightforward integral. Before I integrate, I'm going to pull out all the constants outside of the integral sign. Now let's take the integral. The integral of d theta is simply theta evaluated from 0 to pi. So the result here is what? Pi minus 0, that's just pi. So really this is just equal to pi. So that brings another factor of pi in the numerator that will cancel, not cancel, but simplify the pi squared in the denominator. And here's the final result. Total electric potential at the center of the curvature is equal to capital Q divided by 4 pi epsilon 0 A.